Hello everybody, my name is Ramaprakash. I am an astronomer working at the Inter-University Center for Astronomy and Astrophysics in Pune. My basic interests are in building instruments for astronomy, various kinds of instruments like telescopes, spectrographs, cameras, polarimeters, etc. And today I would be talking about infrared, optical and UV astronomy. The reason why I mentioned infrared, UV and optical astronomy I will come to in one of the slides later. But before we do that, I just wanted to highlight what an astronomer typically is trying to do as part of his routine job. We would call it the 3 F's of astronomy. The first F is about looking at the farthest objects in the universe, how far we can see. We will come to later that the distances we are talking about in this context. Astronomers look at enormously large distances away from where we live on Earth. The second F relates to the faintest objects in this universe. What is the faintest celestial object from which you can collect information and study about. And the third F is the finest, which relates to how fine details of an object in the sky you can study. So, as an astronomer, pushing the limits of these 3 F's, the farthest, how far you can go, the faintest, or the object you can study, and the finest, and how fine detail, how much of details you can study on that object. These 3 things drive astronomy to new frontiers all the time. But today I will not talk about the whole range of electromagnetic spectrum which astronomers use to gather information about celestial objects. I will concentrate only on a very small part of the electromagnetic spectrum, which is highlighted here. The electromagnetic spectrum covers wavelengths all the way from X-rays to radio waves, and it is a very large range of wavelengths, and astronomers use all these wavelengths to study celestial objects. However, for today we would be talking about wavelengths which are very close to what human eye can see, the visible wavelength. Wavelengths which are slightly longer than that, what are called the infrared wavelength, and wavelengths which are slightly shorter than that called ultraviolet wavelengths. So, the topic we cover today will only cover the range of wavelengths in this regime. When we want to collect light or electromagnetic radiation at other wavelengths, the technologies used are very different. The method by which you gather the information is very different, and the kind of information you can gather from celestial objects is also very different. So, astronomers end up using the entire electromagnetic spectrum to study about objects in the sky. But we do not have time to cover that entire spectrum today. There is topic for some other lecture. So, let us come to the main part of today's discussion. As an astronomer, the primary tool which an astronomer uses to look at the sky is a telescope. Our worldview, the understanding of what our world look like changed substantially when about 400 years ago Galileo pointed this telescope towards the sky and started looking at objects in the sky like the sun, the planets, the moon, and so on and so forth, and that revolutionized our understanding of the universe we lived in. And since then, telescopes have been built over the last several hundred years, which are larger and larger compared to Galileo's telescope, and they are the main tools of an astronomer which provide him the right information to study the celestial objects. So, let us try to understand what exactly a telescope does for an astronomer. That is what I would cover in this slide. If you ask a child to look through a telescope, the child would say that object is appearing very close, closer than what you would see when you look with your eyes directly. So, the telescopes are supposed to bring objects closer. Now, let us try to understand what that means to bring objects closer. There are two aspects. One is when an object comes closer, you are going to collect more light from that object. The other part is when the object comes closer, you are able to see more details. For example, if you have a candle which is sitting very far away, about a kilometer away or something, you do not know, you collect very little light from it. You may not even know that there is a candle sitting there. However, if you look at that candle with a telescope, the telescope gathers more light. You start detecting light coming from that telescope, from that candle, and you are able to measure that light and try understand more about that source of light. Similarly, if a person is standing very far away, you do not know who it is because you are not seeing the details, but looking at that person through a telescope, you are beginning to see more features on the face, the posture, and so on and so forth, and from that you start understanding who that person is, what he is doing, and so on and so forth. So, bringing an object closer has two aspects. You are collecting more light from that object, you are beginning to see more details. Now, this you can translate as an object becomes brighter while looking through a telescope, and you see finer details when you look through a telescope. These are the two aspects of a telescope as far as an astronomer is concerned. Now, the diameter of the telescope, the diameter of the primary collecting optics of the telescope, let us say the primary mirror or the main lens of the telescope, is what defines how much brighter an object becomes when you look through the telescope. Similarly, it is the focal length of the telescope which defines how fine a detail you can see using that telescope from a distant object. So, there are two parameters which define the abilities of a telescope, its diameter, its focal length, and they in turn allows an astronomer to do the kind of studies he wants to do, he or she wants to do. So, if you look at Galileo's telescope, it had a diameter of about 40 millimeter, the primary optics. But if you look at the largest existing telescope today, the Keck telescope, it has a 10 meter diameter primary mirror. Similarly, if you look at the focal lengths, Galileo's telescope had a focal length of about 400 millimeters, but Keck telescope 150,000 millimeters or 150 meters. So, you can see that from Galileo's times, in terms of our ability to use telescope to discern objects in the sky, faint objects as well as in great detail, we have come a long way forward. Keck telescopes are enormously more powerful than the kind of telescope people used in the time of Galileo and others. So, this is amazing. We have come forward a long way over the last 400 years. Having said that, let us try to understand what kind of distances are we talking about in astronomy, because we said in the beginning that the telescopes bring objects closer. So, how far away are these objects, so that we can understand what it means by bringing objects closer. We all know that Earth is at a distance from the sun such that it takes about 8 minutes for the light from the sun to reach Earth. So, if I multiply 8 minutes by 60, you get 480 seconds, multiplied by the speed of light, you get about 1.5 into 10 to the 11 meters as a typical distance between Earth and Sun. That is the radius of the orbit at which Earth goes around the Sun. This distance is usually called an astronomical unit, 1 AU. It's about 1.5 into 10 to the 11 meters. You can already see that this is an enormously large distance. However, even this distance is not good enough as a measure for an astronomer. Astronomers use even bigger units. Typically, you would have also heard this unit called a light year, which is the distance light can travel in 1 year. So, in 1 year there is about 3 times 10 to the 7 seconds roughly times this velocity of light, which is 3 times 10 to the 8. So, roughly 1 light year is 10 to the 16 meters, which is already 10 to the 5 times more, almost 10 to the 5 times an astronomical unit. Astronomers use an even bigger unit to measure distances. I am trying to explain that here. So, if I take a stick like this of certain length, and if I draw 2 lines from the 2 ends of the stick such that they converge to a point here, and if you now move that stick farther away, you can see that the angle subtended by these 2 lines becomes smaller and smaller. So, when this stick is close, this angle is this large. As the stick moved farther, the angle becomes smaller, and then if you put the stick even farther away, the angle is even smaller. Now, if I take a stick which is 1 astronomical unit in size, this distance 1.5 to 10 to the 11 meters in size, and then draw 2 lines from the 2 edges, make them converge at one point, and see how far away do I have to go so that this angle is 1 arc second. Now, if you remember, 1 arc second is 1/60th of 1/60th of a degree. That is a very tiny angle. 1 degree, as you all know, is a small angle. 1/60th of a degree is 1 arc minute. 1/60th of an arc minute is 1 arc second. So, it is a very tiny angle, which means you have to go an enormously long distance away from this very large stick to make this angle so tiny. So, that distance is called 1 parsec. So, astronomers use 1 parsec as a measure of distances to objects in the sky. You can relatively easily show that 1 parsec is about 3¼ times a light year. So, 3.25, roughly 3.25 times a light year is 1 parsec. Now, if I ask the question, in the units of parsecs, how far is the nearest star from our sun? Nearest star is called Proxima Centauri. It is about 4.2 light years away from the sun, which is roughly a little more than 1 parsec away. So, this is typical distances from between stars, from one star to another in the galaxy is about 1 parsec. It is a rough kind of distance between interstellar, that is a typical interstellar distance. Now, in those units, if I ask what is the size of the galaxy which we live in, the Milky Way galaxy, it is 20,000 times typical interstellar distances. This is enormous. You can already see the Earth Sun distance is already very large, 10 to the 5 times. That is 1 light year, several light years is a parsec. Now, you are talking about several tens of thousands of parsecs. That is the size of a Milky Way galaxy. If I ask you what the distances to the nearest objects outside the Milky Way, called the Magellanic Clouds, the small Magellanic Cloud and the large Magellanic Clouds, they are about 50 to 60 kiloparsecs away from the center of our galaxy. The nearest galaxy to our galaxy, called Andromeda galaxy, it is about 0.6 megaparsec away, almost 1 megaparsec. So, this is another factor of 1000. It is kiloparsec. The size of galaxy is a kiloparsec or units of kiloparsecs. Now, we are talking about units of megaparsecs, which are typical intergalactic distances between nearby galaxies. And then if you ask what is the size of the visible universe, how far can you see today? It is in the order of another factor of 1000 larger. So, 4000 megaparsec. That is as far as we can see today with the best telescopes, the most powerful telescopes. So, you can see that even Earth Sun distance is very large, and compared to that at every level, interstellar distances, size of the galaxy, intergalactic distances, and the size of the universe, at each stage there are a factor of 1000. You are talking about very large distances here. So, one has to ask, what does this mean in this context by saying that a telescope brings objects closer? These distances are practically infinite, infinitely far away. So, what does it mean by a telescope bringing an object closer in this context? So, let us try to understand that a little bit more. The first question I would like to ask is, if I point my telescope at a distant object like a star, how does the telescope make the star appear brighter? The star is just a point source in the sky, just a point. Now, I put a telescope and look toward the star, how does the light from the star appear brighter? So, to understand that, you imagine a star which is very far away. The light from the star is radiating in all directions away from the star. So, if I think of rays of light starting from the star at same time, after a given time they would have reached a certain distance. So, let us say this far away, they form a sphere around the star. That is how far the light has reached after a certain time. Little time later, all those rays would have reached this far, and so on and so forth. So, if I sit here on the earth and look at that star, by the time the light has traveled this enormous distance from the star to where you sit, you are talking about a spherical surface with a radius which is infinitely large, which means the surface is practically plane. It is the curvature of the surface is almost negligible, immeasurably small. So, if I look at the way the rays are now traveling, the rays are perpendicular to the surface, they are all parallel to each other. So, while the rays are starting out from the star radial direction, diverging, after they travel these enormous distances across the skies, by the time they arrive at earth, they are almost parallel to each other, because this surface is now a sphere of infinite radius, almost infinite radius. So, now I put a telescope here and look at that star. Depending on the size of the telescope, I am going to collect more light from the same star. So, if I have a small telescope, I am collecting this much light from the star. If I have a larger telescope, I am going to collect this much light from the star, which means the star appears brighter. So, the diameter of the telescope therefore makes the star appear brighter to you, just because it collects more light which is coming from that star, more light from the wavefront emanating from that star. Now, let us try to understand how the telescope allows you to see fine details, see structures on galaxies, or details of the change in intensity of light emitting from different parts of a source in the sky. To understand that, let us put a second star here, which is I mark with a red color here. So, the light from this star also is traveling these enormous distances before reaching the earth, but the circles or the spheres are now centered on this star. The light coming from this star, all the spheres are centered on this star, which means by the time they arrive here, the wavefront becomes plane, but now it is slightly tilted with respect to the wavefront of light coming from this star, because this wavefront is centered, the red wavefront is centered on the red star and the black one is centered on the black star, which means the light arriving at the earth from this red star is arriving at a slightly different angle compared to the light from the other star. if the telescope is able to differentiate this slight difference in the angle of arrival of the rays from the two stars, the telescope will be able to see this as two stars. But if the telescope is unable to do that, and if it is not able to measure this difference in the arrival angles of these rays, it will see these two stars as one blob of light. You will not see any detail here. You will be able to see the detail that these are two stars only if the telescope is able to differentiate the angle of arrival of these two the rays from these two objects in the sky. And that ability of the telescope is defined by the focal length of the telescope. So, the mirror diameter allows you to collect more light and make the objects brighter. The focal length of the telescope allows you to see these tiny differences in the angle of arrival of the rays, thereby allowing you to see finer details. So, let us try to put this into a little more quantitative fashion. I represent here with this lens and this lens is an effective telescope. Let us assume this represents a whole telescope. Now, the rays from the star, distant objects at which the telescope is pointing, is arriving in this direction, and from elementary ray optics, which many of you have studied, you can show that all these rays will converge to a plane here at a point which is at the distance of the focal length of the lens. So, if this lens is representing a telescope of a certain focal length, that focal plane of the telescope is where all the rays converge. Now, if it is clear that if I make this lens larger, the object will appear brighter. That is very obvious. So, the diameter of the lens or the telescope is what defines how bright an object becomes. Now, imagine there is another object in the sky which is slightly at an angle away from the first object. So, as we illustrated in the last slide, the rays from that object will arrive at the telescope at a slightly different angle. And again, from elementary ray optics, you can show that all the rays from that object in the sky which is arriving on the lens or the telescope at this angle, this slightly the red rays, they will all converge at a different point at the focal plane of the telescope, which is compared to the first one. So, there is these are the 2 points at which the 2 images of those 2 objects in the sky form. This is the image of the first object, this is the image of the second object. Now, you can see that the separation between these objects is defined by the focal length of the telescope. If the focal length of the telescope is longer, you will get these objects much better separated. I will just do a little bit of mathematics here to show that if this angle, the angle of arrival of the rays between the 2 objects is defined by theta and the focal length of the telescope is f, then this height h is given by f theta is equal to h, which means the angle in the sky theta is given by the separation of the 2 images divided by the focal length of the telescope. So, this theta is expressed in radians. Now, if I convert this theta into arc seconds, these are 206,265 arc seconds in a radian. So, 206,265 divided by f is called the plate scale of the telescope, which denotes what is the angular separation in the sky such that the image separation at the focal plane of the telescope is 1 millimeter. That is defined as the plate scale of the telescope. By setting h equal to 1 and finding what the theta corresponding to that is called plate scale of the telescope, here expressed in arc seconds per millimeter. So, if I know the focal length of the telescope, this number divided by the focal length of the telescope tells you what the ability of the telescope in separating the images of 2 close by objects in the sky, and that is clearly how we see fine details of objects in the sky. So, with this simple illustration, we have clearly shows that the diameter of the telescope objects which makes objects brighter, and the focal length of the telescope which allows you to see fine details in the sky. Now, if you have a telescope, there are ways in which many ways in which you can construct a telescope. I showed earlier slide that telescope is just represented by a lens. So, here is a telescope where it is actually a lens and the rays are focused by the lens, and you put the eye here behind an eyepiece, so that you can see objects in the sky. So, this kind of telescope which uses lenses are called refractor telescopes, because they work based on the principle of refraction of light as they pass through the lens to focus the rays and produce images here. So, these are refractor telescopes, but most of the modern telescopes are based on reflection principle, like here. Here is a reflective telescope where the primary optics is made of a mirror rather than a lens. So, rays from the sky arrive at the telescope, and the primary mirror focuses the rays here, and then there is a small fold mirror here, so that the rays come out and you put an eyepiece there and you look through here. And so, this entire optics is called a Newtonian reflector. There are other ways of arranging optics to build telescopes. In this scheme, you still have a primary mirror here, which is the main collecting optics. Rays arrive here from the sky on this primary optics. They again converge, but instead of a fold mirror as is used here, there is another mirror put here, which is put here, which converges the rays further and focuses them. This primary mirror has a hole in the middle. So, this rays focus at a position behind the primary mirror at the back of the telescope, and this kind of arrangement is called a Cassegrain reflector. And similarly, there are many other ways of producing using multiple optical elements and producing focusing optics. Most of the modern telescopes, the large telescope especially, are reflector based telescopes for several reasons. Primarily, the refractive telescope, as the rays pass through the refractive elements like a lens, the position where they come to focus is wavelength dependent. So, a green wavelength light will focus at one location at the telescope's focal plane, while blue or red may focus at a different location, which means that you will not get a very sharp image at the focal plane of the telescope when you use refractor based optics. On the other hand, the mirrors have no problem, as the rays do not pass through the mirrors, they only reflect from their surface. All wavelengths reflect and can come to the same point at the focal plane, and so this is one of the advantages of reflectors over refractors. And most of the modern telescopes are therefore made by reflector optics rather than refractor optics. So, we have discussed so far how a telescope allows an astronomer to see faraway objects and how it allows you to see fine details. Now, it naturally leads us to a question: is there a limit of how faint you can see? What is the faintest object you can see in the sky? Is there a limit to that? Because can you just go on making telescopes which are larger and larger, and that will allow one to see objects which are fainter and fainter unlimitedly, or is there a limit? So, that is a natural question which arises. So, let us try to address that question in this slide. So, question is, can we see objects fainter than the sky? For example, if you go out in the daytime and look at the sky, you do not see any stars, because the sky is so bright, it produces light which is much more brighter than the light produced by typical stars, and you do not see stars in the sky. Now, is this a limitation? If you go to a very dark site where in the night, if you look up at the sky will still have some light, scattered light from stars, light which are thrown up from our cities, the city lights thrown up into the atmosphere and scattering back. All this light appears to be coming from the sky and make the sky brighter. That is why in a city you will in the night, even in the night, you will not be able to see many stars. You have to go to an extremely dark place where the sky, where the location is very far from cities and the sky is very dark, when you have to see very faint stars. But the question here is the sky, even the dark sky, setting the limit of how faint an object you can see? To illustrate that, let us take a patch of the sky here. I have shown a very dark patch of the sky. I am putting a star there which is bright enough. So, since this sky is very dark, it is night, no moon in the sky. So, you are able to see the star. Now, if I make the star a little fainter, you are still able to see it, little fainter, you are still able to see it, a little fainter, it is not visible. I have not removed that star is still there, because if I make the sky a little darker, you can see the star faintly out there, okay, it is still there. So, as you can see, there is clearly a limit coming from the sky of how faint an object you can see, but is this an ultimate limit? The question is, if I do not see a star here because the sky is bright, but I point a telescope toward that region of the sky and then collect the total light coming from that region of the sky, which is the total light from the sky as well as coming from the star. Then I measure the sky in a nearby region and just subtract the sky off. So, that is easy doable. So, if I can subtract the sky off and just measure the excess light coming in the direction from where the star exists, I can see the star. So, that means that there is no limit. You can just however bright the sky is, you just measure the sky, subtract it, and you will be able to see the star. But this has a limitation. The limitation comes from the fact that you are never able to measure light either from the sky or from the star infinitely accurately. Any measurement of light is associated with an error in your measurement. This is something you cannot avoid. The error always exists in any measurement, and that error in the measurement will define how faint an object you can see in the sky. So, in the case of photons, which are if you are observing the sky at wavelengths which are similar to visible light, UV, infrared radiation, etc., if you collect n photons, let us call as photons as units of light. So, if we collect n units of light from a certain direction, there is an inherent error in that measurement of root n photons. What I mean to say is, I collect n photons in one experiment from a part of the sky. I repeat the experiment again. Next time you will not get n photons, you will get a number of photons which is different from n. And you repeat this experiment many times. Each time you get a number near n, but not exactly n. So, if we take a mean or the average of all those numbers, they will tend to become n, and the spread in those numbers, how much uncertainty, how much error is there in each of those measurements will be given by root n. So, that is the point. This is nothing to do with the measurement technique being used, this is nothing to do with the limitations of the detector or the telescope or the optics you are using. This property is inherent to light. This is the way light behaves. If you collect n photons of light on an average, that measurement is always uncertain to a level of root n. This is coming from physics of the nature of the photons. This is not a result of any of the human process or the technology process. Is inherent. That is the nature of the photons. Now, given this information, let us go back to the question of, can we see objects fainter than the sky? Because you are saying any measurement, there is an inherent uncertainty in measurement or inherent error in the measurement. So, if the light coming from your star is smaller than the inherent error in your measurement of the light, you cannot make a conclusion that there is a star there. If the light from the star is brighter than the inherent error in your measurement, you can conclude that there is a star at that location. So, let us try to understand this a little bit more. So, I make a table here. The first column of the table, I will put some numbers corresponding to the number of photons collected from the star. In the second column is the number of photons coming from the sky. What I call sky here is all the light coming from any source other than the star. So, you are interested in measuring the light from the star. Any light arriving on your telescope from that direction, which is not coming from the star, like the scattered light from the atmosphere or the light from the moon, all that contributes to what I call here a sky. So, all those photons is collected from that extraneous sources is n sky. So, as from the above bullet here, the uncertainty in measuring the star light is the root of this number n star. So, this column will have root of this number, and the uncertainty in measuring the sky light is given by the root of this number. So, this column will have the square root of that number. And what I call the signal to noise ratio is the ratio of this number above this total uncertainty. So, signal is the signal from the star, the total photons you collect from the star, and the noise in the denominator is the total of the noise coming from the star measurement and the sky measurement. So, if this number is larger than 1, it means that your signal is much larger than the noise or your error in measurement, and you will be able to see that there is a star there. If this number is smaller than 1, you will not be able to see the star, you will not be able to detect the star, because the noise or the error in measurement is larger than your signal. So, let us look at this scenario where there is a star in the sky which is emitting, let us say, 1 photon per unit time. The sky in that direction is emitting 100 photons, 100 times brighter sky. So, clearly the uncertainty in the measurement of the photons from the star is 1, root of 1 is 1. Uncertainty is measurement of the sky is 10, because it's square root of 100. So, the total noise is roughly 1 over 10, because if you put 1 and 10 in this formula, it is roughly equal to 10. So, 1 by 10. So, clearly the signal to noise ratio is much less than 1, you will not be able to see that there is a star in that direction. However, if I make a telescope which is 100 times larger and look at that same direction, now I am going to collect 100 times more photons from the star. Of course, the sky also will become 100 times brighter. Now, the error in measurement of this 100 photons from the star is only 10. Error in measurement of this 10,000 photons from the sky is 100, which is square root of this. So, the total signal to noise ratio now is signal of 100 and the total uncertainty of 100 here. So, the signal to noise ratio is 1. So, clearly your star is just being able to detect at this point. The signal is at least as equal as your measurement error. If I make a telescope which is 100 times bigger, so this now I am going to get 10,000 photons from the star itself. Of course, the light from the sky also is 100 times larger, but now the uncertainty from the sky is 1000, but the light you are collecting from the star is 10,000, which means your signal to noise ratio is 10,000 over 1000, 10. Now, the signal is 10 times stronger than your measurement error, you will begin to see the star. So, clearly making a telescope larger and larger will allow you to see objects which are fainter and fainter, and therefore, although the sky sets a limit on how faint an object you can see in the sky, by collecting more and more photons, by developing larger and larger telescopes, or by staring at the same direction and collecting more of the photons, so that this n becomes very large, you would be able to reduce the noise or the uncertainty in your measurement to a small enough number that you should be able to see the faintest objects as faint as you want. The sky does set the limit, but if you are resourceful, you can beat the sky. That is a message. So, having said that, let us look at a different aspect of astronomy. Let us look at some real telescopes, where they are and so on and so forth. Here is the location, one of the world's best astronomy locations, where you can see a large number of telescopes. This is a mountain called Mauna Kea. It is an extinct volcano in one of the Hawaiian islands, at a mean height of about 4,200 meters above sea level. So, this height is about 4 and bit kilometers above the surface or the mean sea level. So, you can see many observatories there. These are the twin Keck telescopes. I mentioned Keck telescopes in one of the first slides, the largest existing optical telescopes in the world. There are 2 of them in this location. This is the 8-meter Gemini telescope, this is the 8-meter Subaru telescope, then there is a Gemini telescope, etc., etc. So, the very large telescopes, many of them are located at the top of this mountain. Now, why is this mountain special? First of all, this mountain is so tall that most of the time the clouds are below this mountain, which means when you are looking up at the sky, the clouds do not block the light coming from those faint objects in the sky. You are above the clouds. There are other reasons. I will come to some of those reasons later, but astronomers take enormous efforts to identify locations which match many of the requirements they put to call a site as an excellent site for astronomy. Of course, cloud cover is one of them. There are other factors which we will talk about a little later. So, this is just a close-up view of the twin Keck telescope. You can see the 10-meter primary mirror inside. There are 2 of them which are separated by about a few hundred meters apart, and this is located at Mauna Kea. There are various ways in which telescopes can be mounted. We talked about various ways in which telescopes are made in terms of optics, but that is only one part of the sky, one part of the story. When you want to point the telescope at the sky, it is just not enough to just point at a particular direction. The sky is moving. We all know that objects, including the sun, the stars, the moon, all of the objects in the sky appears to rise in the east, go across the sky and set in the west. So, if you want to collect light from a distant faint objects, you have to point the telescope at that object for a long time. You have to maximize the number of photons you can collect, you want to collect from that object to see faint objects. So, which means that the telescope has to track the movement of that object in the sky. And there are 2 ways in which there are many ways, but there are 2 very common ways in which telescopes are mounted, so that they can track objects in the sky. One of them is shown on the left side. It is called a altitude azimuth or alt azimuth mount. What is done here is you have let us call a vertical mount on which the telescope tube is mounted, and So, the telescope tube is able to rotate on two axes. One is this axis around the base of the vertical mount, and the other axis is this horizontal axis into the plane of the paper where I am pointing here. So, the telescope is able to move in this direction or this direction, two axes of movement. So, in this condition, one of the primary axes is normal to the surface of the location at which the telescope is mounted, that is vertical. There is another way of mounting the telescope, which is called the equatorial mount, in which the primary mounting axis is pointing towards the direction of the celestial pole. Now, what is the celestial pole? The celestial pole is the direction in the sky at which the axis of rotation of the earth seems to meet the sky. So, earth is rotating about its axis. If you project that axis of the earth into the sky, that axis appears to meet the sky at some location. That location is called the celestial pole. So, if you mount your primary mounting structure with its axis pointing towards the celestial pole, and then the telescope is again able to move along an axis which is horizontal, which is pointing into the plane of the paper in this axis, that is called an equatorial mount. So, in this condition the main axis is not vertical, but it is pointing towards the celestial pole. Both of them have advantages and disadvantages. In this condition, there are multiple axes to be moved simultaneously to keep track of an object in the sky, while in this condition if you point the telescope at an object and just rotate around this axis, just this axis, you will track an object in the sky. So, only one axis needs to be moved, but this orientation has to be aligned perfectly with respect to the celestial pole in this configuration. So, they have advantages and disadvantages, and both kind of mountings are used for astronomical telescopes depending on the situation. Now, here is another telescope which is a 5-meter telescope. You can see the primary tube of the telescope here, the primary mirror is here at the back. It is a Cassegrain telescope. If you remember, I explained the Cassegrain telescope in one of the earlier slides. It is a Cassegrain telescope. So, the light from the distant object comes through the tube here, falls on the primary mirror, converges, goes to a secondary mirror here and converges further, and through a hole in the middle of the primary mirror comes to the final focus at the back of the primary mirror. And this is an equatorial mounted telescope. On the other hand, here is another telescope which is main tube which is mounted vertically. Here the main mount is pointing at the pole, here the main mount is pointing at vertically. So, this is an equatorial mounted telescope, while this is an alt-azimuth mounted telescope. There is another set of telescopes in the southern hemisphere. Each of them are 8 meters in diameter, and there are 4 of them. This is located on a mountain in Chile near the Atacama Desert. These are called the Very Large Telescope, built by a consortium of countries in Europe, and is operational from this Chilean mountain. So, if I draw a sketch of all the large telescopes which are currently existing, these topmost row shows telescopes which have diameter about 4 meters. These are 8 and 10 meters diameter and so on, and the blue ones are in the northern hemisphere and the yellow ones are in the southern hemisphere of the earth. So, you can see that there is a large number of very big telescopes which astronomers have constructed over the past several hundred years. If I look at the number of telescopes which are smaller than 4 meters in diameter, there are several hundred of them. I cannot fit them all in this slide. So, these are only the largest among them. Now, we are in an era where astronomers are now planning to build the next generation telescopes which are even larger. There are 3 of them being currently planned. The first one is the Giant Magellan Telescope with an effective diameter of about 25 meters. Nobody can make a single piece of glass, either a mirror or lens, which is 25 meters in diameter. So, this telescope primary mirror is made of 7 8-meter diameter glass pieces. So, each of these mirrors are 8 meters in diameter. You put 7 of them together to form one telescope, which is effectively 25 meters, roughly 25 meters in diameter. There is another one called the 30-meter diameter telescope or 30-meter telescope. Here you can see the primary mirror of the telescope. Instead of using large mirror segments which are smaller in number, the 30-meter telescope uses smaller segments, each of them are hexagonal in shape, about only 1 meter, 1.4 meters in size, but you have about 500 of them arranged together to form a 30-meter diameter primary mirror. And there is an even larger telescope which is effectively 39-meter diameter, again made of small segments. You can't see the segments because segments are so small compared to the big size of the primary mirror. So, this telescope is made of about close to 1000 segments, which are about 1.4 meters in size and hexagonal in shape. They are arranged in edge to edge to form a 39-meter primary mirror. So, these are gigantic telescopes which are being built or planned to be built at various locations around the globe, and they are going to revolutionize astronomy in the next decade. The kind of discoveries they are going to make, the kind of new understandings of celestial objects they enable are going to be unimaginable. So, we are really living in an era where astronomy is on the cusp of a revolution in terms of discovery capability. So, if I take one of those telescopes like the Keck telescope and put a circle there to indicate its size, and take the European extremely large telescope which is 39 meters in diameter, you can see the jump in your ability, the light collecting ability of this telescope. You can almost fit all the existing telescopes kind of within this area of this large telescope, which means that your light gathering power of astronomers is going to enormously increase once these telescopes become operational over the next decade or so. And equivalently, these telescopes also have very large focal lengths, which means they will be also able to find exquisitely fine details of objects in the sky. So, as I said at the beginning, it is not enough to just point the telescope at a part of the sky. It is not sufficient to have the telescope stationary pointing at a part of the sky, because the sky itself is moving. What is shown here is the trajectories of the objects in the sky. So, this is the celestial pole which I mentioned earlier. All objects in the sky appear to travel along trajectories which are circular and centered at the celestial pole. This is easy to understand, because the reason why objects in the sky appears to move is really it is not the sky which is moving, it is us sitting on the earth and going around as part of the rotation of the earth about its axis, which makes the sky appear to move. So, clearly if you sit on the earth and rotate about an axis, and if you look out at the sky, the objects in the sky would appear to form or move in trajectories, move in paths which are symmetric with respect to the point at which the axis of the earth would hit the sky. So, it is very clear, simple to understand that those symmetric trajectories would be circular orbits in the sky. So, when a telescope has to point at a sky, we know that in 24 hours the earth rotates 360 degrees, which means in 1 hour it rotates 15 degrees. In 4 minutes it will cover 1 degree of rotation, which means that if you look just heads up into the sky, every 4 minutes later you are seeing a part of the sky which is 1 degree away. So, every minute the sky moves by 15 arc minutes, with 1 arc minute again is 1/60th of a degree, and every second the sky appears to move by 15 arc seconds, which is again 1/60th of an arc minute. So, when a telescope points at objects in the sky, this is a time lapse movie which shows how a star actually appears to move across the sky. They form these kind of tracks, which means the telescope which starts pointing at this object here has to keep moving in a way that it tracks the movement of that object in the sky, and so on and so forth. If we start pointing at this object here, you have to point the telescope continuously in a way that it tracks this movement, and that is how you are able to collect as many photons as you need from that object. So, this is just a illustration of how a telescope moves. This is a model of the Gemini telescope, one of a very large telescope. The primary mirror diameter is 8 meters here. So, you can see the base of the telescope moving. So, this is the base, and since this base is perpendicular to the local vertical of this ground, this is an alt-azimuth mount as I explained earlier, and the tube of the telescope, as I explained earlier, can move up and down. So, between the base movement and the tube movement, you should be able to point at 8 part of the sky. So, the telescope would move at least on these 2 axes to keep track of objects in the sky. Now, the point to keep in mind here is this is an enormously large structure. This mirror is 8 meters in diameter. The glass is several thousand tons, several thousand kilograms, several tons heavy. They have to this mirror and the secondary mirror at the top of the telescope, the 2 mirrors which form the images, they have to be very well aligned as the telescope moves around. So, this entire moving mass is several thousand kilograms, tens of thousands of kilograms moving mass, and this moving mass has to move very accurately to point at that objects in the sky as they move across the sky. It is an enormous engineering challenge to make this happen, and this is not set up in a laboratory environment. It is sitting out there on the top of a very high mountain, exposed to elements like the wind, the temperature changes, the vibrations, all kinds of disturbances which can destabilize it, and in the presence of all those disturbing conditions, this gigantic structure has to very accurately point at parts of the sky, and while at the same time keeping this parts of the optics exquisitely aligned with respect to each other. So, this is a very large engineering challenge. Astronomy is driven, when you want to make larger and larger telescopes, astronomy is driven by the technological advances which allow these enormous machines to be built on top of these big mountains. So, this is just a list of things which illustrates what all the telescope has to do. It has to track objects in the sky at the rate at which the sky appears to move. It has to, in spite of moving at that rate, it may need guide stars in the sky to make sure that the tracking is accurate enough, and it has to do this tracking in the presence of various causes which can lead to misalignments, like the gravity. So, when the telescope is pointing vertically up or horizontally or toward the lower direction, the effect of gravity on this optics and the entire mechanical structure is very different, and this can misalign things. Temperature changes, wind, all this is going to affect how well a telescope can operate in that environment. In addition to that, there is this set of effects caused by the atmosphere. The light which is coming from these distant objects, while it travels almost all the time through almost empty space, it hits the atmosphere and it has to pass through that atmosphere before it can reach the optics of a ground based telescope. The atmosphere leads to a set of effects which can affect how good your image is. I will illustrate that here in a slide here. So, if we think of the ground layer here, this ground is heated by solar radiation, human activities, then the wind could be blowing across. So, all this is mixing the atmosphere up all the time continuously. So, the atmosphere through which the light has to pass through is not a very homogeneous stable medium. It is a turbulent inhomogeneous medium which is continuously changing because of all these factors. What it means is that the atmosphere when it receives this energy from various sources like the heating of the ground, heating from the sun, the wind, etc., the energy which is injected into the atmosphere at large scales, because of the relative movement of the different parts, tend to break down into smaller and smaller eddies. What I am trying to say here is, at large scales energy is injected by the sun, the earth, etc., into the atmosphere. The wind blows the air across, and because of all these movements, the energy injected initially into large scale motion of big parts of the atmosphere will break up into smaller and smaller parts which are independently moving relative to each other. That is natural, because atmosphere is not a solid, it is a gaseous thing. So, the energy gets dissipated into smaller and smaller features into the atmosphere to a level where it becomes so small that they can then, because of viscous forces, etc., becomes negligible at that point, and then they can retain as one blob of atmosphere. So, there is structure in the atmosphere at all scales, at the scales at which the large scales at which energy gets injected, all the way where the blobs break up into smaller and smaller parcels of atmosphere into the smallest scale. And this is continuously changing. It is not that this piece stays like this all the time. This next instant of the time, some other part gets mixed with this, and then the shape of all the blobs keep changing, and this is a continuous process. And this leads to what is called atmospheric seeing. As light passes through the atmosphere, which is disturbed like this. For example, if you have an ocean here, on top of which this atmosphere and the wind is blowing, there is very little disturbance or turbulence in this atmosphere. But if there is a mountain on the path which disturbs that flow, the atmosphere can get very turbulent on the other side of the mountain. And what happens is, when light passes through the atmosphere, if it is passing through this part which is very smooth flowing, you can see exquisite details of objects in the sky. On the other hand, if this light is passing through part of the atmosphere which are turbulent, what it leads to is that the image quality deteriorates, and the details which you can see of celestial objects considerably deteriorates, and this effect is called atmospheric seeing.